Good morning to all. Myself, Professor T.M. Diwakar, working as a assistant professor in Department of ENTC in Sharad Institute of Technology, College of Engineering, Anji. So today I am going to cover the short circuit and open circuit in a network analysis. So let us see. So in the network simplifications, these short circuits and open circuits plays very important role. So what exactly the short circuit? So this is the diagram of short circuit. See here what exactly the short circuit. When any two terminal or points in the network are joined directly to each other with a thick metallic conducting wires, the 2 points are said to be short circuited. See here, this is the network, okay, and here are the 2 points A and B, okay, and these 2 points A and B, they are connected with a thick conducting wires. So these 2 points A and B are called as a short circuited, and the resistance of such short circuited is 0. See here, RAC is equals to 0. RAC means this is the short circuit resistance is 0. The next part is the point A and B are short circuited. So the resistance of the branch AB is also called as a branch, is 0 ohm, and the current here IAB, the current IAB is flowing through the short circuited path. So using the Ohm's law, we can calculate what is the voltage across the terminal A and B. So we know that the Ohm's law, V is equals to I into R. So now we are calculating the voltage across the terminal AB. So VAB is equals to R into I. So what is R? R is the short circuit resistance. I is the current flowing through this circuit, short circuit. So what is the value of R? R is nothing but 0. So 0 into the current I is equals to 0. So in a short circuit, the voltage across the short circuit is always 0, though the current flows through the short circuited path. So you just remember that in a short circuit, the voltage is always 0, but the current flowing through the short circuited path. You just remember this one only. Next one is the open circuited. So what exactly the open circuit? When there is no connection between the 2 points of the networks, means here A and B, these are the 2 points and there is no any connections, but having some voltage across the 2 points. So the terminal A and B having the voltage, so these 2 points are said to be the open circuited points. So as there is no direct connection in an open circuit, so there is no connection between the terminal A and B, so it is a open circuited. The resistance of the open circuit is infinity ohm, okay, and there is no current flowing through this open circuited. See, that's why the I is equals to 0 is given here, okay. So let us come to the point. The points A and B are said to be open circuited, okay, and the resistance of the branch AB is infinity, okay. So there exists a voltage across the points A and B called as open circuit voltage. So there exists a voltage across the point A and B, so it is called as a open circuit voltage, that is a VAB. So according to the Ohm's law, I is equals to V upon R. So I is the open circuit current, VAB is the voltage across AB and the resistance of the open circuit. So we know that the resistance of the open circuit is infinity and voltage across the terminal AB. So therefore the current through the open circuit is 0. So this is the key point. Just the current through the open circuit is always 0, though there exists a voltage across the open circuit terminal. You remember here that in open circuit there is no current flowing through the open circuit, and there is a voltage across the terminal A and B. You always remember. Okay, see, once again I am repeating, in a short circuit, okay, there is a current flowing through the short circuit and voltage is 0, but in an open circuit there is a voltage across the terminal but current is 0. You just remember these 2 points. Okay, next, these are very important points. What exactly called as a redundant branches and combinations? So see here, because while solving the network we also know that what exactly the redundant branch. So see the definition of the redundant branch. If in a circuit there are the branches or the combination of the elements, see, if in a network or if in a circuit there are the branches or the combination of the network which do not carry any current, and then such branches and combinations are called as a redundant from the circuit point of view. Understand? So once again here I am repeating what exactly the redundant. Redundant is nothing but it is a branch or it is the combination of the elements there no currents is flowing. Understand? So the redundant branches and the combinations can be removed, and these branches do not affect the performance of the circuit. So while solving the network simplifications or while solving the network or the circuit, we should have to remove the redundant branch. So after removing, it will not affect any performance of the performance of the circuit. That is called as a redundance, because there is no current flowing, so there is no effect on the performance of the circuits. Okay, but there are two important situations of the redundancy which may exist in the practical circuits. So situation number 1, see here, situation number 1. Okay, so any branch or combinations, okay, across which there exists a short circuit, okay, so become redundant as it does not carry any current. Okay, see here, so in figure number A, okay, so R3 is a branch, okay, and there exists a short circuit. Okay, see here, this is the short circuit, okay, across the branch R3. So the current does not flowing through the branch R3, so it is bypassed. Okay, and hence the branch R3 is a redundant branch. Okay, next one, if in a network there exists a direct short circuit across the resistance or the combination of resistance, then that resistance or the entire combination of the resistance become inactive from the circuit point of view. Such a combination is redundant from the circuit point of view. Okay, so see the figure number 2. This is the figure number 2. Okay, here R3 and R4. Okay, so these are the combination of the elements and across which there is a short circuit. Here it is a short circuit. Okay, see here, this is the short. See here, the resistance R3 and R4 means this is the branches R3 and R4 across which the short circuit is exist. This is the short circuit. So the current is flowing through the short circuit path. So these branch R3 and R4 or this is the combination of the resistance are the inactive. and and therefore there is no current flowing through this combination of the resistance, and these two combinations are called as a redundant from the circuit point of view. Okay, so as I explained you now in figure number 3, there is a R3 is a redundant branch because the current always prepares the low resistance path, hence the entire current I passes through the short circuit, and hence the resistance R3 becomes a redundant from the circuit point of view. Okay, let's come to the diagram. So this is the diagram. Okay, see here the total current I is flowing R1, R2 and through the short circuit. Okay, so there is no current flowing through the R3. Okay, so R3 is a redundant branch. Okay, next there is a short circuit across the combination of R3 and R4. So entire current flows through the short circuit across R3 and R4, and that there is no current can flow through the combination of R3 and R4. Thus that combination becomes meaningless, or it is inactive from the circuit point of view. So such combinations are eliminated while analyzing the circuits. Okay, so see here. Okay, the current is flowing from R, okay, R2, and it is flowing, okay, directly from the short circuit path. So there is no current flowing through the R3 and R4, so it is a negligible. Okay, next one, situation number 2, which exists in the network regarding the redundant, if there is a open circuit in a branch or the combinations. Open circuit means there is no any connection between the branches, so it cannot carry any current, and it becomes the redundant. See here, so in this example, this is the branch, there is exist open circuit. Open circuit means the branch B and C, this is the branch. Okay, so branch BC and branch CD cannot carry any current. Okay, so it becomes a redundant from the circuit point of view. Okay, so there are two situations. Number 1, if there is a short circuit across any resistance, if there are a combination of resistance and they are across a short circuit, then that branch or that combination of circuit is a redundant. Second point is, if there is exist any open circuit in the branch, so that branch becomes redundant from the circuit point of view. Okay, so it is very important. Next, the voltage division in a series circuit of a resistance. Okay, as we know that, okay, in a series there are a voltage division, and in a parallel there is a current division. So let us come to the point, the voltage division in a series circuit of a resistance. Okay, so consider a series circuit of two resistors R1 and R2. So resistors R1 and R2 are connected in series with a source of voltage V. Okay, as two resistors are connected in series, the current flowing through R1 and R2 are the same. Okay, so you can apply the KVL law here. So what is the KVL law? Already we studied the KVL law. See here, we get V is equals to, KVL means it is a Kirchhoff's voltage law. The sum of all the voltages is, the algebraic sum of all the voltages is equals to 0. Okay, so here exist, first of all we just find out the voltage exist in the network. So V is a voltage source, this is one. Second one is voltage across resistance R1, that is a VR1. Next, third one is the voltage across resistance R2, that is the VR2. See, so by using Ohm's law we know that V is equals to I into R. So resistance R1 and R2, in these two resistance the same current is flowing. So voltage across resistance R1 is equals to VR1 is equals to I into R1. Okay, and VR2 is equals to I into R2. Okay, so here then applying KVL law. Okay, phi is equals to I into R1 plus phi is equals to I into R1. So therefore the total current I is equals to phi upon R1 plus R2. So the total voltage applied is equal to the sum of voltage drop phi R1 and phi R2 across R1 and R2 respectively. Okay, so see here, now we have calculated the total current I, so you can just substitute this value in phi R1. So phi R1 is equals to, here I means phi upon R1 plus R2 into R1. So the voltage division in voltage across R1 you can calculate is equals to R1 upon R1 plus R2 into the total voltage. So the voltage across resistance R1, we can calculate the resistance of that point upon the sum of the resistors into the total voltage. Okay, next point, similarly you can calculate phi R2. Okay, phi R2 means it is equals to I into R2. We know the value of I, total current we have calculated, that is a V upon R1 plus R2. Okay, so that's why the voltage across R2 is equals to R2 upon R1 plus R2 into V. So this circuit is called as a voltage divider circuit. Okay, so let us see the key point. In general, the voltage drop across any resistance or the combination of resistors in a series circuit is equals to the ratio of that resistance value to the total resistance multiplied by the source voltage. See here once again, the voltage drop across any resistance. Here I am taking one example. The voltage drop across the R2 is equals to the ratio of that resistance value to the total resistance. Ratio of that resistance means R2. Okay, the R2 upon total resistance is what? R1 plus R2, and it is multiplied by the source voltage, that is a V. Okay, next point is current division in a parallel circuit of a resistance. Okay, so in a parallel there are a distribution of currents. Okay, let us see the diagram. There is a voltage source, from that current is throwing, that is the it is the total current. So there are R1 and R2 resistance and they are connected in a parallel. So the current I1 is flowing through R1 and current I2 is flowing through R2. Okay, so here we have to calculate the I1 and I2. Okay, so let us see. So consider the parallel circuit of two resistors R1 and R2 connected across C. The R1 and R2, they are connected across the voltage source V. Okay, the current through R1 is I1 and current through R2 is I2. So while total current drawn from the source is IT. Okay, IT is the total current and which is drawn from the V voltage source. Okay, so total current IT is equals to I1 plus I2. See here, this is I1 plus I2. Now we have to calculate the I1. Okay, how you can calculate the I1? I1 is equals to phi upon R1 and I2 is equals to V upon R2. Okay, that means V is equals to I1 R1 and V is equals to I2 R2. Okay, so therefore I1 is equals to I2 in bracket R2 upon R1. So substituting the value of I1 in total current IT. Okay, see here. So therefore total current IT is equals to I2, because I2 is nothing but the value of I1. See, this is the value of I1. Here we have to substitute the value. This is in this case. Okay, so this is IT. Okay, so IT is equals to I2 in bracket R2 upon R1 plus I2. Okay, so total current IT is equals to I2 in bracket R1 plus R2 upon R1. Okay, similarly you can find out, okay, I2 and I1 here R2 upon R1 plus R2 into total current IT. Okay, so let us come to the key point. So what exactly the key point in the parallel circuit, current division in parallel circuit? Okay, the current in any branch is equals to the ratio of the opposite branch resistance to the total resistance value, and it is multiplied by the total current in the circuit. Okay, means just observe this current. Okay, it is very simple. Okay, suppose if you want to calculate current I1, so what exactly the key point? So I1 is equals to what is the total resistance, sorry, what is the opposite resistance of this R1? R2 is the opposite resistance. So R2 divided by what is the total resistance? R1 plus R2. Okay, so how to calculate current I1? So current I1 is equals to R2 upon R1 plus R2 into multiplied by total current IT. So see here, okay, so current I1 R2 is nothing but it is the opposite resistance of that R1 divided by the total resistance, that means R1 plus R2, and it is multiplied by total current IT. So this is the formula. Similarly you can find out total, you can find out the current I2. How you can find out? See here, I2 is flowing through resistance R2. So what is the opposite resistance of R2? R1 is the opposite resistance. So what is the total resistance? That is R1 plus R2, and into multiply by what is the total current? That is the IT is the total current. So how you are going to calculate I2? I2 is equals to, see here, okay, R1 is the opposite resistance divided by R1 plus R2, it is the total resistance, into multiply by total current, that is the IT. So similarly we can find out I1 plus I2. Okay, see here, let us solve one example based on the voltage division in series circuit and current division in parallel circuit. Okay, so this is the circuit, one example I am taking here. So find the voltage across the three resistance. Okay, so we have to find out the voltage across each resistance, means voltage across R1 is nothing but VR1, voltage across R2 is nothing but VR2, and voltage across R3 is nothing but VR3, and the total voltage source, it is given that 60 volt. Okay, so as we know that the Ohm's law you can apply here for each resistance. So what is the Ohm's law? And see here, already we know that all these three resistors are connected in series. So in a series there is only one current flowing through all the resistance. So total current I is equals to I. Okay, before that, first of all we have to calculate the current I is equals to phi upon R. R means it is equivalent resistance. So equivalent resistance is R1 plus R2 plus R3. Okay, so V, it is already given 60 volt. See here, phi is already given 60 volt divided by the values of R1, R2 and R3 they have given 10 plus 20 plus 30, that is the 1 ampere. So total current I is equals to 1 ampere. So what is the voltage across resistance R1 is equals to I into R1. So already we have calculated the total current I is a 1 ampere. So the value of R1 already it is given. So 1 into 10 is equals to 10 volts. So voltage across R1 is equals to, see here, 1 into 10, because 10 is the value of resistance R1 multiplied by I. Okay. Similarly, you can find out the voltage across resistance R2, that is I into R2. We know that the value of I and value of R2. So 1 is equals to 20, that is a 20 volt. And see, similarly you can find out the voltage across resistance R3, that means I is equals to I into R3. We know that the value of I and R3, that is the value of I is 1 into value of R3 is equals to 30. So you can just cross multiply, you can just verify it. Okay, see here the value of VR1, VR2 and VR3 is total 60 volt. Okay, and the total voltage source value is 60 volts. So based on the KVL law, the algebraic sum of all voltage is equals to 0. It means it can be verified that the KVL law here. So key points here, key point, it can be seen that voltage across any resistance of the series circuit is the ratio of that resistance to the total resistance, and it is multiplied by the source voltage. Let us take one more example. Here we have to calculate the current I1 and I2. So find the magnitude of the total current and total IT. Okay, so current through R1 and R2, if the value of R1 is 10 ohm and the value of R2 is 20 ohm and the total voltage is given that 50 volt. Okay, already we studied the current distribution in parallel circuit. So this is the current distribution. Okay, so first we have to calculate the I1. How we are going to calculate the I1 here? See here, already by using the formula, I1 is equals to opposite resistance is R2 upon total resistance R1 plus R2 into the total current IT. Okay, so we don't have the value of total current IT. So let us first of all, you can find out the value of IT. How we are going to find out the value of IT? So IT is equals to V upon R1 plus R2. Okay, so we already given the value of R1 and R2, we already known it. Okay, so let us see. First of all, you can find out the IT, that is the V upon R equivalent. So R equivalent means what? There are two resistors, no? Then they are connected in parallel. So this is the formula you can use, R1 into R2 upon R1 plus R2. So this is 10 into 20 divided by 10 plus 20. So value of R equivalent is 6.67. So total current IT is equals to 50 upon 50 is nothing but that is the voltage source, total voltage source. They already given 50 volt upon 6.67. So total current IT is equals to 7.5 ampere. Okay. Here you can apply the current distribution law, as I already said that I1. How you can find out I1? The total current IT upon the total resistance, opposite resistance R2 upon R1 plus R2. You just substitute the value of IT, R1 and R2. So the value of I1 is 5 ampere. Similarly, you can find out the value of I2. We are going to find out here the value of I2. The opposite resistance is what? R1 divided by R1 plus R2 into the multiplied by the total current IT. Okay, so see here, opposite R1 is the opposite resistance divided by R1 plus R2 and it is multiplied by the total current IT, and we know that the total current IT is 7.5 ampere into, okay, the value of R1 upon R1 plus R2 is nothing but 2.5 ampere. So it can be verified that total current IT is 7.5 ampere is equals to I1 plus I2. I1 is 5 ampere plus I2 is 2.5 ampere. So this is also equals to 7.5. So total current IT is always equals to the sum of individual currents. Okay. So thank you.